we'll talk about language generation in the limit. And the plan is I'll first walk you through the notation. I'll remind you what identifiability in the limit was. I'll give you a few basic examples, simple examples. Then I will talk about generation in the limit. I'll give you a few more examples. Then I'll give you a hard instance. It's like a fake, I don't know, stupid hard, I don't know. It's a hard instance where identifiability fails. Then we will see how language generation on that hard instance is not that hard. Then we'll discuss some algorithm for language generation and other properties. Okay. So I guess let's start with notation. So this is big sigma is the alphabet set which contains some characters, finite set of characters. So for instance, in English this could be A to Z. Then you have a set of strings which contains all the possible finite combinations of these characters. So I denote that by U, and you might remember this notation. So essentially this contains all possible combinations. So for instance, it contains all the single letter strings, all the 2-letter strings, all the 3-letter strings, and so on. Makes sense? All the strings are still finite. Okay. And you can imagine that this will, if you're talking about English, this will contain all characters, it will contain all words, it will contain all sentences, paragraphs, textbooks, encyclopedia, like everything. Everything's there. And the nice thing about this structure is that you can map it to natural numbers. So for instance, you can assign this 1, this 2 until 26. This can be 26 plus 1. Here it can be 26 plus 26 squared, and so on. You get the idea. Now what this allows us to do is get rid of all this, and I just say U is equal to natural numbers. So I can work with this now. That's nice because I don't have to talk about these complicated strings. I can just work with natural numbers. Okay. Then you have this language. This idea of language. Language is just a subset of natural numbers. So one example of of a language could be all even numbers. And again, if you like this representation, you can map these numbers back. So I guess 0 is missing, 2 is B, and 4 is D, and so on. Okay. And finally, English examples. English is also a language which will contain A, B, C, D. So 1 to 26. Then it will contain the number representation of words such as cat, dog, and so on. Okay. So language is just a subset of N. Makes sense. All right. And yes, just a few more things. This is a strict subset, and this is a subset equal to. So it need not be strict. So I guess if I were to pictorially draw it, this means this, and either of those. Make sense? Yeah. Okay. I'll define identification in the limit again. Again, it's called notation. So now I have this U. I'll also have a set of languages. So I'll denote that by X. This is a countable set of languages. Each of which is a subset of the natural numbers. Okay, now this is a game played between two players, the adversary and the learner. I'll denote adversary by ADV. So I'm the adversary and you are the learner, calligraphic A. And what I'll do I'll pick one of the languages from X. So say I pick K. I pick K from X, and then I start enumerating strings from K. So, or natural numbers from K. And your goal is to identify which of these languages is K. If you can do that with zero error after some time, then we'll say that you have identified the language and limit. So at round T, I'll give you WT, which comes from K. K is coming from X. So you see all the languages that I've generated so far, denote that by capital WT. And you generate some output. So call that OT. No, sorry. You generate an index of one of these languages. So say you generate IT, and then your guess for the language is LIT. Okay, makes sense? And if there is some time after which LIT is always equal to K, that's called identification in the limit. Okay. Let's go through some quick examples, and then we can talk about generation. So this is example 1. X is n. This is the language. N is the language, and X is a singleton set. So I'll pick K from n from X, and then I'll start enumerating strings from the language that I picked. Okay, so I pick K. I don't tell you K, and then I start generating strings. So what's your guess for K?
N.
N? Makes sense. Okay. What about now?
Just
Same thing.
Same thing, right? It's a single language. Okay.
I know the set of language. I know X, like.
You know X.
Right. Okay.
Okay.
This is trivial.
Huh? This is trivial, yes. All examples are trivial. Okay. I think that's the beauty, right?
That's the beauty.
Okay. Let's try one more. So 0, 1, 1, 2, 2, 3, and so on. You get the idea. So X is a set of finite languages, but X itself is infinite. Okay, I'll pick K, I pick K, and I start the enumeration process. So I give you 1. So what's your guess? This is L1, L2, and so on.
L1.
Okay, so L1, of course it's wrong. I give you 1 again.
L1.
Yeah.
Again, it's wrong. So you see, if I keep giving you 1, you won't be able to identify the language clearly. So
Sorry, in the feedback you don't say it's wrong. You
oh,
don't
yeah,
have any feedback.
I should mention that.
Right.
Sorry. Okay. So you get no feedback.
I see.
I'm giving you feedback because
It's
I
more
want
fun.
to show that I'm a real adversary. There's no feedback.
Okay.
Right. Oh, there's one more thing. There's this model of computation. So, or Oracle, if you like to call it, if you'd like to call it that, at each time you can perform this. You can ask, is WT in LI for any I? So you can ask, you can do this membership query. So for instance,
But you just said that we do not get feedback, and this is feedback.
you do not get feedback about whether Li is equal to K. Your guess is equal to K, but you do get this. So you can, if I give you 1, you can ask, is 1 in L1, is 1 in L2, you can ask that.
So basically we know X and all the elements that are in each
Yes.
subset of X,
Yes.
or each element of
Yes.
X. Yeah.
If you are wondering why this is important, so recall that a language can be an infinite set of strings. So checking if something is there, say, okay, this is your language. 1, 2, it's just positive numbers. Checking if 0 is in this set is unwieldy. Like, what will you do? You check, okay, 0 is not this element, 0 is not this element, 0 is not this element. You keep on going, right? So I guess this Oracle takes care of that.
I might have missed it, but what literature or papers is this talk based on?
Okay, I never talked about it. So, I guess a little bit cold. I spoke with Roshan for quite some time. So if the talk seems good, it's because of Roshan's feedback. If it's bad, that's on me. Then there was this talk by Kleinberg at IAS. That talk was nice. I learned something from there. And I mentioned some results. So I put this document on Slack. You can find it there. The main papers are Kleinberg and Mullainathan, 24, and Kleinberg and Shi, 25. I guess this is the main reference. Okay.
In like 2024, you're not 1924.
Yes. Yeah. This is something. This is 1960 something. Okay. Yeah. Right. Anyways. Okay. Back to our game. So there'll be an assumption going forward that if I pick K, I will be generating all the elements of K eventually. So if I had picked say L1, I would at some point generate 0. Make sense? Okay, so continuing with the game, I picked 2. Now what's your guess?
L2.
L2. Makes sense, and it doesn't matter after this. There's only one possibility. There's only a single language which contains both 1 and 2. Okay, this shows that finite languages are easy. So of course, moving forward, we'll be considering infinite languages. Fair enough? Okay, I'll bore you with a few more examples and then we'll move forward. Okay. This time X is set of even, odd, and all natural numbers. So I have 3 languages. Okay. And now I'll start enumerating. Okay, I didn't write the example here. 0. So you make some guess. Of course it will be wrong because I'm the adversary, right?
Even.
Okay, so you guess even. Alright, then I make another guess, 2. Even. Probably see where I'm going with this. 4.
Even.
Even. I'll never show you anything else. And you would be wrong.
Except we don't know.
Kind of, yeah.
I thought you said part of the rules was that every letter in the language or every element in the language has to get shown.
Yeah.
So then the sequence that you gave, if it was L3, it would never show all the elements of L3.
Right.
I mean, it will after we've shown all of L1.
No. That's not how it works. I guess, okay, maybe I think I misspoke. I guess this example shows that there is no this example shows that there is no a priori bound on how much time it will take for you to identify the language.
Okay.
If it's identifiable. Good point. That's why we have the hard example. Right. Otherwise, this would have been the hard example.
This is the easy example?
These are the trivial examples, I call them. Trivial identification examples. All right. So you might ask that why is there an adversary?
So here in this example, we couldn't identify actually.
Oh, so I guess a very nice point was that if either the language is even, it can't be odd. Either the language is even or natural numbers. If it is natural numbers, then eventually I'll see an odd number here.
Okay.
So I'll be able to identify it. But the point that I should have made in the first place was that there's no a priori bound on how much time it will take for you to identify it.
Isn't the naturals infinite though? So like,
Yeah.
couldn't you just not see an odd?
So when I say that you'll see all the elements of the language at some point, that's saying you pick an element from the language. This is just writing it in math, maybe this will help. So I pick some string from the language, then there exists some time t such that wt is equal to w.
So this is an assumption on the adversary.
Yes.
Okay.
Makes sense. I guess I didn't really explain it. I just wrote it in. So you pick 3 here, 3 here. Then there should be a time after which 3 would be shown, if n is actually the chosen language.
Oh, okay.
Recall the simple example from last time. It's gone now. Or this one. If I drop this assumption and I keep generating from from L1, right?
Yeah.
You cannot identify if it's L1 or L3, right?
Yeah.
But if I add this assumption, you would be able to identify it in the limit.
Okay.
Makes sense.
Yeah.
But it's like kind of weird because like if you generate them in the order that you generate all the evens first and then you generate all the odd ones, then you generated a countably infinite number of things before
Right.
you move to odd.
Right.
But then you would have, I thought the identifiability thing was like only after a finite number of things
Yes.
you then eventually
Right.
stop outputting
Yeah.
the wrong thing, but this time you wouldn't,
No,
right? You would have had
You
to go
wouldn't
through
be able to do
countably
that.
infinitely many things that you got wrong.
so this is the assumption. I don't have a name for it. Let's call it, you see everything assumption. So if you pick 1, for instance, 1 is an odd number which is in n,
Yeah.
L3. So you would see 1 after a finite amount of time. If I were to enumerate all even numbers, then this would
Yeah.
not hold.
I see.
Okay, maybe I should write it here. So model of computation, this is what the algorithm has access to, and then adversary is operating under the you see everything assumption. Okay, then I wanted to make a comment about why are we using adversary. So I guess the idea is that no matter what algorithm you pick, there is the adversary can make the language set unidentifiable. So this is same as saying that no matter what algorithm you pick, there would be a problem instance. When I say problem instance, I mean this set K and the enumeration sequence. So there exists a problem instance which your algorithm won't be able to identify.
I guess the language class is fixed, right? So it's only the text that is under the control of the adversary, right? The infinite text. Language class is kind of agreed to beforehand by everyone. Right?
Okay, yeah. It doesn't matter, right?
No, because like there may not be an algorithm that works on some arbitrary language class, but the algorithm may be specialized to the language class. The only thing that's under the control of the adversary is the sequence of things that it's going to show the algorithm, and it can pick that based on the algorithm.
Right. Okay, maybe I'll summarize that quickly. So you need both an amenable language set and an amenable, or it works for all amenable language sets. This is what Roshan is saying, I guess. Enumeration is the key here. Okay, anyways, let's move on. So now we'll talk about generation, and we'll keep this example in mind. Generation is similar, very similar. You still have an adversary. You have x. I choose k. At each time step, I give you wt. The only difference is, instead of outputting your guess of k, you output a string from your guess of k. So, for instance, at time step t, the algorithm guesses it, and then the guess is lit. Then the algorithm would, instead of outputting lit, the algorithm would output a string from lit. So, say ot from lit. So this is the output. As long as ot lies in k, that's the correct response. And if you can, after some finite amount of time, keep generating strings from the correct language, then you have generation in the limit. Make sense? Okay. Few more examples. I I have some other examples before moving on to this nice one. So x is unknown. You don't.
I have a quick question about what you said there. So in this case, if it's responding something from the LIT, what if that data T belongs in both languages in this case? And then
That's fine, as long as it also belongs in K, that's fine. There's one more thing I'll mention that after this example.
Oh, okay.
So this is a cute example. You don't know X, and I choose K from this X. Of course, X is a countable set of languages, and all languages are infinite. Okay, I'll give you the string 0. Can you generate a string from the true language?
Yes.
And what would the guess be?
Zero.
0. Okay, makes sense. What if I give you 3?
3.
0 or 3. You have 2 options now, and so on. So clearly, this can hold for anything. This is not interesting, or it's interesting, but we already solved it. So our winning criteria or our required criteria would be that the language you generate should be from the true set minus whatever the adversary has already generated. So you want to generate new examples. It's not just a memorization task. It has some flavor of identifiability inside. Okay, let's go to another example. Okay, I guess it's this one now. So we are looking at the same example, this time under generation in the limit scenario. Okay, so I give you a string 2. Now you make some guess. Then I give you 4. Now can you make a guess?
6.
6. Okay, that's a correct guess, because 2 and 4, they can only come from either L1, which is the set of even strings, or L3, which is all natural numbers, and 6 lies in both of them, right? Okay, and I give you 6 now. Can you make a guess? 8, and so on. So you see, this problem was kind of weird under identifiability. Not quite, we have a real hard example coming. But under generation, it seems much simpler.
What do we do with the question mark?
Oh, you can output anything. Say you outputted 1. So you were wrong here, but after this time,
In the limit, yeah, okay.
yeah, this is the limit. After t equal to t greater than equal to 2, you're generating in the limit.
Why would you output 1 if you saw 2?
Because you thought that it's L3. Okay, maybe Roshan is not happy. Let's change it to 0. So then, from the beginning, you're correct. Okay. Any questions about the second? Okay, I'll give you the hard example now. Actually, you were late, Diego. Do you know this, or do you don't know any of this? Okay, let's do a quick recap.
No, it's okay.
Are you sure you won't be able to understand the?
I try to use inference.
Okay.
In the limit, he'll understand.
He can't, right? That's the thing. See, I even added a bullet point, number 17, that you cannot really identify an algorithm from its trace. So, I don't know if we'll be able to do that. If we believe in all this, I should go over it. Okay, there you go, half a minute version, and other people can correct me if I'm saying something wrong. This is a game that's being played between an adversary and algorithm. You're the algorithm, I'm the adversary. I choose a set of languages. Okay, you remember what a language is? Perfect. So I choose a set of, there's a fixed set of languages, I call it calligraphic X. I choose one language from it, K, I fix it. Of course, I'm not fixing it, I'll change it based on what you tell me, but it's fixed. at time step t, I'll output a string from k. So at time step t, you would have seen all these strings that the adversary gave you. And each time step, your goal is to output some other string which the adversary did not output. So it can't be one of these strings, but it has to come from the true language k. So this is your success criteria.
So in that example, we could not have outputted 2 because it was already.
Yes, if you output 2, that's not success. Because then you can solve it like that. It's not interesting anymore. Like ChatGPT loses all its creativity. I believe it is creative. Okay, let's discuss this at the end. Obviously, I don't know what I'm talking about, but it's nice to add some stories. Okay, now I'll give you the hard instance from Gold's paper. I'll admit that I don't quite appreciate it, but I've memorized it. So at least I'll be able to show you what it is, and we can discuss. All right. So here's the hard instance. I'll create a set of languages starting with L0. L0 is the set of all numbers, but ignore 1, 0. Let's just start with 1. Okay, L1 is the set of all powers of the first prime number. So the first prime number is 2. So all powers of 2 would be 1, 2, 4, 8, and so on. Then I have L2. L2 is the is different powers of the first 2 prime numbers. So 2 and 3.
Fundamental theorem. It's going to be the fundamental theorem of arithmetic gives you.
There's no fundamental theorem here.
Yeah.
No, there's none. But you're thinking of prime factorization. That prime factorization exists or something. I guess I will be using it. You're right. I'll write an equality, and that requires you to prove something. But we won't be doing any of that. So 2 times 3 would be here. 2 squared times 3, and so on. You get the idea. So Ln would be the first n prime numbers and all possible powers. Okay. Should I write it down or? I'll write it down. That was Roshan suggested that just write things down. So I'll enumerate the prime numbers as P1, P2 until Pn. Powers would be G1, G2, Gn, and Gi are here. Make sense? Okay. Now I want you to appreciate that this, starting from here, this is an increasing sequence of sets. So L1 is contained within L2, L2 is contained within L3, and so on. All right. And I guess the fundamental theorem comes here. So union of all these is L0. So if you take the union of all these, you recover all the natural numbers. Make sense? Okay, and X is of course L0, L1, so on. All right. So we'll play the game first for identifiability, then for generation, and this will show that identification in general is not possible. In particular, identification is not possible in general for countable set of languages. Okay. So I'm the adversary. I pick a language. So this is what I'll do. I'll start by picking L1, and I start enumerating from it. Okay. So I enumerate 1, 2, 4, 8, and so on. Okay. So what guesses can you make? You can make any guess. If you make a guess which is anything other than L1 or L0, you will be wrong, right? Okay, makes sense? Because if you guess L2, then of course I will never show you 3 here. Like based on this information, guessing anything other than L0 or L1 is like doesn't really help you. Remember, the goal is identification. You need to identify which language am I enumerating from. In my head, it's L1. Of course, I don't show you this. Okay, so let's say case 1.
Does GI can be 0?
GI can be 0. Yes, natural numbers start from 0.
So let's say L2 also fits in if GI equals to 2, which is defined what means?
You can never have, if you guess L2, since you saw 4, you would be wrong.
That's why I'm asking, can GI equals to 0?
Actually, L1 is the subset of all of the language.
Yeah, sorry, this is plus.
Okay.
Okay, that's why I wrote it here. Okay, yes, plus, it's a plus. Thanks, Eric. Okay, this is plus.
So L1 and L2 doesn't have 1.
Yeah. It's not quite an increasing set of languages.
So each prime number is only in L, like whichever L to N.
No, wait a second, sorry. No, okay, sorry. The notes are wrong. There shouldn't be a plus there. It's N. It's N.
And includes 0?
Yeah.
Yeah.
Doesn't matter.
Because you switch, right? I'm guessing, like, as soon as they guess L1, you switch to a different one. To like
Yeah,
L2.
we're not there yet. The confusion is before that. So, if you guess L2, you are consistent with the data, but you're wrong. Because if you say L2, I would say no, of course you're wrong, because the language is L1.
Or you could be wrong.
You could be wrong.
You're not sure you're right.
Right.
And each language is a subset of the next language. and
Yeah.
stuff.
So it's identifiability, right? If you kept guessing L2 forever, you have not identified K, which was L1. Okay, so what is the game that I can play? I cannot change the output that I've generated, but I can, since I do not tell you K, I can change that arbitrarily as long as I'm consistent with the output that I already showed you, right? Like, I'm not a fair player. So if you kept generating L2, then you are not identifying the language in the limit. Make sense? Okay, we'll do this. I pick K equal to L1 and I generate the sequence and you keep outputting L2. Is the identification in the limit problem solved? No, right. What about L0? So if you pick anything other than L1, the identification problem is not solved, right? Okay. So of course, we'll move on, and this is what you were alluding to. So now, say at some point, the algorithm guesses L1. As soon as the algorithm guesses L1, then what I'll do, I'll switch this. I'll say, oh, this was 2. And now I'll start generating something like 3. You see? So of course you were wrong. Or I don't even need to generate 3. I can just say, oh, it was L2 all along. I'll have to generate 3 sometime because of this you see everything assumption. Go ahead, Brad.
So can't you just start with the lowest L that's not L0, and then every time you see something from another one, you just add the next one up?
Yeah.
And you'll be fine.
No, you'll never be able to identify the true language.
Why?
Because, okay, say you guess L1 here, what do you guess here?
Well, imagine you guessed L1 from the beginning,
Okay, yeah.
but it doesn't really matter. Then you move to L2 as soon as you see something outside of L1.
if you kept
Like basically the moment you change from L1 to L2,
right,
I change to L2 as well.
yeah,
And I can keep following you.
yes, but in the end I'll say, oh, the true language was L0.
But like, I guess I must have seen everything from L0 at some point though. And that would have allowed me to identify that it's L0 and not L infinity or whatever.
No, you can't.
Like there's gotta be some point where you see something in L0 that's not in the largest L.
This is
in
infinite
finite
times.
times.
All the languages are infinite.
And there's infinite languages.
No, like there's a difference between L0 has things that L1 doesn't.
Yeah.
Right? And L0 has something that every Ln.
So every language is a subset of all the languages
That's
after
right.
it,
And
and
there's
L0 is a
strict subsets.
superset of all of them.
That's right. But they're strict subsets is what I'm alluding to.
Yes.
And so what
And
I'm
the
saying is
union
that,
of all of them is exactly L0.
right, and what I'm saying is that if you actually chose L0, if the adversary actually chose L0, then it must in finite time generate something from L0 that's not in any of the other languages.
But there is no such thing.
Mhm.
So every element of L0 is in some other language. That's what that says, the union thing over there.
That's true. Is it true?
Mhm.
Because for
But like-
every element of L0 is a natural number,
Yeah, I guess
so you
that's
can prime factorize it, and then there's a biggest prime factor, and so it's going to be in that set.
If you want, I can play this game again. Let's spend some time playing this game. I don't
But
tell
it's kind of
you.
weird.
It is. I agree.
Because now you have, like, something feels very wrong. Like, you know what I mean? Because the claim you said is like that you're gonna generate a W, like it says in the box. You're like, I'm gonna generate at some finite time a WT from that language.
No, I think the difference is, I think what you're thinking is that it sounds weird to say that the adversary is switching, but actually the adversary is not switching.
No,
The
I agree with
adversary
that.
is simulating what the learner would have done.
Yeah.
And if the learner at some point would have switched to L0 and stayed on L0, then the adversary can just say, no, you're wrong, because actually I was thinking of L100,000 or something. But if on the other hand, the learner was just going to stick to one of the L100,000 or whatever, then the adversary would say, no, actually I was thinking of L0.
I think he appreciates that.
No, I agree.
His,
Yeah, I guess that's interesting because you would just keep going up.
Yeah,
and
so you
up.
can force the adversary to keep switching, or you can force a learner to
Yeah.
keep switching an infinite number of times, which means the learner will never converge, and so it can't identify the limit.
And if that happens, I'll claim that I was generating from L0.
Yeah. If you convert to
Yeah.
L0, you will claim you are generating from something else. If you convert
Yeah.
to something else, you will claim you are generating from L0.
Yeah, I agree. It doesn't. I'm not happy with it.
No, it's not wrong. It feels almost like cheating. Like, what is this telling you? This is like a stupid example. that's how I felt about
So
it.
how should we think about the stupidity? Where should the stupidity land?
Right.
Should it land on the example,
so-
or should it land on the adversary, or the model, or what?
Yeah. So I wrote here, emphasize that even though this example is stupid, it shows identifiability is not possible for countable set of languages. That's it.
Maybe the idea here is that, like, at time step T, we do have, like, we do know, we can see, like, the element from the language. It's just that there exists at least two languages which have that character, that.
Right.
Yeah.
Right.
That's probably the point, at least
Yeah.
two languages, and we cannot, like, discern anything between.
Like, I can always claim, the adversary at any point can claim that so far you have not been able to identify the correct language. So recall that the guarantee is there exists some, say, T star. There exists some point in time after which, so for all T greater than T star, you have identified the true language. So LIT, your guess, at time step T is equal to K. Adversary can break this. Right.
Can you explain that assumption again about what the adversary has to do again? Like that it has to output something from the language. That box?
Adversary has to output every string at least once, at some point, at some finite time. So I cannot selectively, say, for instance, I could do this, right? Say the language is even, I just keep giving you 2.
Yeah, I understand.
So adversary has to enumerate the entire language.
Yeah, so the adversary has to select a language and then produce an infinite sequence that contains everything in a language.
Yeah.
But it can decide which sequence based on what it knows the learner is going to do.
Yeah.
I mean, this, even,
So there's not going to be any T where the adversary is stuck with one L. I mean, it still would have a scope of switching to
Right.
false with the learner.
Yeah,
Right.
that's one way of looking at it.
Right.
Another way of looking at it is you fix the algorithm and you run it on all possible problem instances. There's this one problem instance where this is the behavior you observe, right? So this is the idea. When you have an adversary, like you think about, I don't know if you guys remember, lower bounds, sorting lower bounds. The sorting lower bound by comparison based sort is n log n. The way you prove that is the same thing. If I give you some problem instance, and if you take less than n log n comparisons, then I can switch the problem instance, and then you have failed. So there are two ways of thinking about it. One is adversary is switching things, or you can just say that adversary is switching things based on what you are doing, right? That's one way of looking at it. The other way of looking at it is you fix what you are doing, then I show you, and you run this fixed algorithm on all the possible problem instances. In some problem instance, you won't be able to identify.
And I guess another way of looking at it is there are two texts, there is a single text that could have come from two languages.
Right.
So if you can construct one text and then you say, okay, one instance it came from language 1 and the other instances came from language 2. And the learner will either pick language 1 or language 2
Right.
on this text. And whichever it picked, then it would have been wrong on the other.
Yes.
Because the text is exactly the same, the learner cannot pick two different things on the two different texts.
Right. Precisely. I think this is a good way to put it.
Sure.
Let's solve this instance for generation. So you see this data, and now you are in the generation in the limit framework. Can you generate an example? Can you generate an example string which would be inside the true language? So let's start. 1. Say, what's your guess for 1? I guess you guess, say, 6. So you're wrong here. It's possible that you're wrong. You see 2, and then you see 4, 8. Once you have seen, say, these 3, I guess, then you can just start generating even numbers, right?
No, power of 2.
Huh?
The power of 2 numbers.
The power of 2. Yeah, sorry. Then you'll be fine. Does everyone appreciate that?
Yeah.
So it's
we
like,
should have done that from the beginning. All of them have power 2s.
yeah,
You don't even need to see anything.
that's true.
So this first concept was identifiability, and what is this called?
Generation.
Generation.
So you're not trying to identify the true language. You're just trying to generate a string from the true language that the adversary has not shown you before.
Wait, can I just, the claim they had before was that we show that there exists a set of countably infinite languages for which we cannot identify, right?
There exists a set of, yes, this set.
Yeah. There exists a set of countably infinite,
Yeah.
And now, okay, you're showing that this is not a hard example for generation.
Yes. You can do generation in the limit for this example.
Because L1 is the subset of all of the languages and it's infinite. So we always have a new sentences to generate.
Yeah.
And we are sure that this is gonna be in the correct language too. I see.
Yeah. I guess Vlad is reminding me that I'm not saying that this shows generation is easy. This is just an example.
I was gonna ask if it goes the other way, I guess every time, if you can identify, you can definitely generate, right?
If you can identify, then you can definitely generate, yes. If you can generate, there are cases where you cannot identify.
This is one of those cases.
So, okay, this would be the complete thing. If you can identify, then you can generate. But if you can generate, then you cannot necessarily identify.
I guess it's a tiny middle, which is that if any other languages are finite, then you might just run out of things to generate, because the adversary can just list all of them and now you can't do anything. Right?
No,
So
this
we
was
are-
an assumption that
all languages
all languages are infinite.
Okay.
Uh,
And we didn't make that. We didn't need to make the assumption in the identification. section.
even there, if we did not make that assumption, then things would be easy.
Right.
That was the 0, 1, 1, 2, 2, 3 example.
Right.
Make sense?
So I have a question, maybe
Mhm.
let's say I is always, is the union of finite numbers, right?
Sorry, what?
I is finite,
I?
yes.
Oh yes, these are this is the countable set. So it's precisely this L0, L1, L2, L3.
Yeah, because I'm not sure, if n goes to infinity, this
Mhm.
one gonna be uncountable.
Oh no, I guess if I write it down, then you'll see it right away. So
The set of numbers is countable, right? So any subset of it has to be countable.
L0,
Yeah, that's.
Even
L1,
if it's
L2,
countable.
L3.
That's the,
So now I'll map this to 0, this to 1, this to 2, this to 3, and so on. And this is natural numbers. So I have a 1-to-1 mapping and onto, what is it called, surjective? I have a surjective mapping between x and natural numbers. That's the definition of countable, right? So this is countable.
I'm thinking L infinity, but so.
L is itself infinite, that's true. So, okay, there are two questions. One, is L itself a sequence of countable strings? Yes, because each Li is a subset of natural numbers. So each language is a sequence of countable strings. And I think I understand your confusion, I'll get to it. And the sets we are considering, they are also countable. Each language is infinite and countable.
Yeah, and the countable union of countable sets is also countable. That's.
Countable. Why to be concerned about that?
I think that's what Seating was worried about.
Oh, I thought sitting was worried about this. So check this out. Pick any string in language. Is it finite or not?
It's fine.
It's finite.
Yeah.
Any string in language is finite. Any string in English is finite, right? Have you ever seen a textbook which is never, I mean, you get the feeling that it never ends, but it does end. You can flip the last page and it ends.
So there's can I maybe like draw a little
Go for
symbol
it.
or because really feeling it this is like the standard that's okay, let's put it up here. So the idea is like let's say you got some L1 and this is some right, so this is like x1, x2, right, so I just write these as little dots, right, so these are all the possible numbers that belong in L1, goes off countably, and then L2, same thing, and these dots need not be the same, they're all just different dots, right, and then this keeps going for infinity, and I'm going to claim that the union of all of these is still countable. So there's a countable union of countable sets, and to do that I just have to claim that, yeah, so it's like the diagonal thing, right? So I can kind of go in this order. This is my first number, this is my second, this is my third, this is my fourth, fifth, sixth. So you kind of go in this order, right? And so on. So you can just number every element of every set in this order. And now you know that eventually you will, no matter which set you pick, and no matter which number in that set you pick, you will eventually get to it in this ordering. So that means the union is also countable.
I understand this part, but I will talk about this later.
And then the other reason you have to think that it's countable is that everything is a subset of natural numbers to start
Yeah.
with, so you can't take one countable case anyway.
Makes sense. Okay, maybe this wasn't your question, but I should mention it since I've written it now. It took me a while to probably go through this every 3 years, and then I understand it again. So n star, this is the clean notation, we know it. This is the set of all finite substrings of n. So this set contains 0, 1, 2, 0, 1, 0, 2, the same thing that I did for characters. This is countable, right? n to the n contains something else. We're not dealing with this. Languages are not coming from here. This contains n star plus infinite strings.
And that is an uncountable.
That's uncountable. Again, why don't we care about this? Because what textbook can you show me which is infinite? So everything is countable. We're only considering language itself is finite, but each string in the language is finite. Language is infinite, each string is finite. Does that make sense?
I think that's the question I was asking.
I'm already nailing it. I forget that this gets recorded, that's why I usually don't record the talks. Okay. Yeah. I mean, I think this happens, right? You bring actually good people. They are super humble. You bring quacks like me. At least I didn't bring myself. That's on Charles. Okay. I hope this was clear. Now we'll move on to. I want to show you the algorithm that does identifiability, and I'll do it first by giving you something which looks correct, and I want you to think for a moment what's going on. Okay, I shouldn't have told you that it's not correct, but okay, let's start. So generation in the limit, and you're given x, which is L1, L2, and so on. Oh, I should mention one more thing. So x is not a set, it's a sequence. This ordering is fixed. Okay. And but I'm making it a set in the sense that no language can be repeated. You can drop this assumption, but let's say there's no repetition of the language. And it's a sequence. This ordering matters. Alright, so now what happens? You will see data. So W1, there's some k that has been fixed, which is unknown to you. You see W1, W2, W3, and so on. Alright, I'll present an algorithm and you should think about it. So this is the algorithm. I first output L1. This is my output. I output a string from L1. There's a time mismatch, but that's okay. Let's just roll with it. So I output a string from L1. When I see, this is how I do. I check is W1 in L1. I first do this. I check is this string in L1. If it is, then I choose L1 and I output a string from L1. Okay. Then I move to W2. If W2 is in L1, I stick with L1 until I see a string which is not in L1. Make sense? So say at time step 2, W1 is again in L1, W2 is in L1. So I'll stick with L1 and then I'll output O2 is in L1. Okay.
Sorry, we are in the language identification.
Generation.
Right? Generation. Okay.
Right. This is what I'm outputting.
Okay.
So until I say at time step 3, I find that W3 is not in L1. So then I switch to L2.
Or maybe L1, I ran out of, for example, words in L1. For example, L1
They're
is
all infinite.
Okay.
We cannot run out of
Okay.
words. Yeah. So as soon as I see something which is not in L1, I switch to L2, and I start generating from L2. So I keep moving forward, and I stop only when I see a language which is explaining everything so far, and that's the algorithm.
So when you say you stop, that means your search. So if the first word was not in L1, then you would, it's not in L2, then it's not in L3, but you would just keep going until you found a language that it was in.
Right.
So you will always be correct, right?
eventually.
Or you won't necessarily be correct, but you will always be consistent with the words you've seen so far.
Right.
You'd also need to verify all the previous sentences came from the language as well in each step of your algorithm, right?
Right. I'm missing something.
This is
Forgot.
arbitrary.
What's
W1, W2, W3.
Like you stop until you find that's consistent.
Capital W before you use it.
I think you can run an infinite.
Capital
algorithm.
W3 is
Okay, not
okay.
this stuff.
Maybe I should write that.
Oh, okay.
No, you just stop at the first instance, because you have an ordering on your languages, so the first instance where it matches with all the previous sentences that you received.
And you just do it infinitely.
I guess
No, and then you just
this
choose
works.
that, and then you see the next one, does it work?
And then
Oh,
I
I see.
move
And then you just,
to,
oh, it doesn't, so
okay.
just keep walking down the list until you find something, next one.
So like it could just like not work infinite times, but you just keep choosing. Oh no, because it's finite. It's x finite.
Why are these subsets?
X is not finite. So Paul was making the point that maybe I should write this. All these things that I've seen so far, are they all a subset of the current current candidate? If it is, then use that. If it's not, move first.
It is sentences.
Capital WT equal to the union of W1 to WT?
Yeah, W3 is capital WT is this set
Oh.
or sequence, whatever.
Is there any relationship between the L's? Like, is there any guarantee that I can increase and find one that lines up with the previous observation?
There has to be.
No.
Because
K is
there's-
chosen.
Because the adversary has to pick a language and it has to generate things from that language. So there is some language in the list that matches everything that the adversary showed you.
That's an assumption. Like maybe the adversary has no way to win. So
It's like this. So let's say there's some language LZ which is K. So Z is the index such that LZ is equal to K. That's the true language. Make sense? And then LZ plus 1 and so on. Okay, this is the language. So, okay, I think it's clear enough, thank you. So, at each time step I check if the capital W, this capital W set is in my current candidate language. If it's not, I'll move forward. Make sense? Okay, this is the algorithm. And why this sounds so appealing is, once you hit LZ, will you ever move forward? No, right?
No.
So you'll get stuck here. So this is nice. I keep moving forward, and as soon as I hit LZ, I'm there. I stay there, and I keep generating from this. So seems correct, right?
And I guess the nice thing is that the ordering also doesn't matter. Like the learner could have picked the ordering, right? Like it doesn't have to be something that the world has to give you. Any ordering you pick is going to work for this.
Yeah. I'm fixing the ordering, but you're right. I'm just simplifying things.
But
for
when
this,
you say you are fixing the ordering, you could be the learner. The learner can fix the ordering.
no, sorry. As an expositioner, I'm fixing the ordering
Okay.
for this presentation.
Right.
You should go first.
Okay.
Siddharth.
Yeah, just to clarify, when you switch the language, if WT is not in it, then you start from the beginning, right?
No, I go to the next language. So I start, my first candidate is L1.
No, but I mean, you start like the sequential order when you see if W1's in L, Z, let's say, you start from the beginning.
Beginning.
Well,
Beginning of your
you
list
know
of
those
words.
languages don't work.
Look, this is, look at this. Consider this big, I think this is why the paper wrote this as ST. These are two different things. This is capital W, this is small w. Okay? So, that's why the size.
Size doesn't matter.
Okay. There was a quip here. No, I pick a candidate language. I start with my first candidate language is L1.
Okay.
Now I see what data I observe. Is that consistent? Let's call it consistent. Let's build some vocabulary. So, this
Okay.
data that I've seen is consistent with my candidate if that data could have come from this language. Makes sense?
Yeah.
Okay, so I check if my data is consistent with the current candidate. If it is, that's nice, I keep the candidate, I ask for more data. If the data is not consistent with the current candidate, I move to the next one. Now why this is appealing? Because once I hit LZ, which is K, I will never move forward.
But how do you know that LZ is consistent with the first?
Oh, this is the thing, I should have written this down. So LZ is K, and all data is coming from K.
I think the question was if you get more data, a language that was inconsistent can never become consistent, right? That's just like the property of consistency, right? So seeing new data is never going to make an inconsistent language consistent because it's already been ruled out by some data.
No, but you only check the consistency with the old language. You get a new language. How do you know that new language
There is no new language. There's only one language.
Okay.
You just didn't know which language it was.
Oh, okay. That makes sense.
Okay. So I'm sure if you think about it, you'll eventually figure it out. I was able to figure it out, so I'm fully confident you can. But it took me like days, so can't wait for days. Right?
Doesn't this have the same problem as the thing where we need it to identify languages? Where this is the algorithm I was proposing earlier, where you just take L1 and then eventually it doesn't work, you pick L2 or the next best one. But you're never gonna.
I think you're probably right.
Z won't be fine.
Right. Okay. I'll draw my nice diagram and then you can tell me if this is exactly what you're thinking. I believe you are.
I have an idea. So there could be the case that LZ minus 1 contains like all the elements from LZ, or like maybe.
I think this is what Vlad was mentioning.
The same thing? Are you?
Yeah, I mean, you can just take the ordering of the previous example. I think.
The thing is that
That's the answer. Okay, let me draw a nice diagram. I spent some time thinking about this. So these dotted triangles, they show LZ, and then I'll draw a square inside. This shows WT. Of course, the square should always be inside the triangle. And what if L1 was this language? See the problem? I'll never move beyond L1 because L1 will always be consistent with the data will always be consistent with L1. However, when I'm generating strings from it, it's possible that I might generate something from here. Right?
Does the learner know the relationship between L1 and LZ? Let's say, does the learner know that L1 is bigger than LZ?
It can know that. The problem is it doesn't know LZ. Okay, to answer your question, no, because it does not know LZ.
If it doesn't know LZ, then how do we move to LZ?
Oh, we keep moving forward. So imagine that these sets were all increasing. So say this was L1, L2, or there was something like this. Finally, until I hit LZ, and I'll draw WT at each time step. Say initially WT was this, but later WT was this. Sorry, this is L1, candidate, right? So at time step 1, the data that I see is consistent with my candidate, so I don't move forward. At time step 2, the data that I see is not consistent with my candidate. So I move forward in the hope of finding LZ. But once I've hit LZ, then I'll never need to move forward.
I guess my question is, if we do not know LZ or L1, how do we know it doesn't fit into our? Do we know some rules or?
We only know how to check membership. So I can check if WT, small w, I can check this. Capital WT is if it's inside a language.
I see.
And the argument in favor of this wrong algorithm was that once I hit LZ, I'll never move forward. That's true, but the problem is perhaps some language before LZ contained LZ, then you would be stuck there.
But that's fine.
That's not fine because as soon as you generate a string, so this was the protocol. You had some candidate language, and then you were generating strings from that candidate language. So if you generate, now you don't know this dotted line, so you might generate strings from here, which would be fine. You might also generate strings from here. If you generate a string from here and you're never moving forward, then you're not generating in the limit.
So the goal is to get the green rectangle, right? And in this case,
Goal is to always generate from within this triangle.
within the triangle.
Yeah.
So you can never move beyond L1, is what you're
Right.
saying, yeah.
Okay, multiple questions. Let's start here.
Just for my understanding, at time step 2, the green square would be a bit in L1, right?
Yeah. Yes. I'm sorry. Okay. Vlad.
I was gonna say, isn't the obvious thing your learner just orders things such that all things that are supersets of other things come later? Like you can change this ordering and that's.
Can you? I guess you can't order an infinite sequence.
What do you mean? It's count to the infinite, doesn't have order.
There's not an absolute ordering on sets. Like you could have them all have like.
No, I understand if they're disjoint, but as long as you don't have any set that's a strip, like a superset of a set later on, you can do that.
Take a topological order.
We do create that in some of the fancy algorithms that I'm not going to talk about. We don't do that here. I guess what you're saying is, should we do that? Absolutely.
No, but I don't mean, yeah, but I'm not sure that's even gonna solve the problem.
That would solve the problem.
Okay, maybe we'll talk about
Okay, it's like, of course it will solve the problem, right? This is like 100,000 things lie in creating these sets. If you do it the right way, interestingly it solves the problem. This is non-trivial. It's if you are interested, you should look at the last section of Kleinberg sheet. I can talk about it with you later. Happy to do that. ML theory, we can talk about it in ML theory. Okay, makes sense? We understand this algorithm doesn't work. Alright, what I'll do, I'll quickly, do you want to learn about the actual algorithm or doesn't matter?
We don't have time.
I mean,
Yeah.
but here, for example, if we had the nested structure of the L1, L2, whatever,
Then it will
then
work.
yeah.
We might not have that. The algorithm will still work. Okay, let's try. If you're, I think we should do it. I came up with this triangle diagrams to explain that. So what I'll do, this is the algorithm. I call it KW for authors, KX. No, it's Way. Kept saying she. It's KW. Okay. The paper is Kleinberg and Way, not she. I guess I know someone named Fan, and the author's name was Fan Way, so I conflated. It also happened with me. I always conflate Emily Kaufman with Katja Hoffman. Both are in Europe. Both do decision making. So this is the algorithm. What you do, you consider at time step t, you consider the languages, all the languages from L1 to LT. Okay, so that's your consideration set, and you will be outputting you will be selecting one of these languages to generate from at time step t. Okay, now I'll introduce this concept of strictly critical sets, strictly critical languages. So a sequence of languages is strictly critical if sequence of languages is strictly critical if all of them are consistent at time step t. All of them are consistent with the data. And they contain they are contained with the strict supersets, subsets. So if this is L1, like this is smaller than this. So this set is a strictly critical set because each language in this set, say consider language L3, then L3 is consistent with the data, plus L3 is a strict subset of all languages before L3 which were also consistent with the data.
Do they have to be subset or? can
This
they
is
just-
this is the definition.
Oh,
So if these two things are satisfied, then the sequence is called strictly critical.
How is this different from a decreasing collection of sets?
It's not.
Okay.
I guess this point, like it's consistent with the data.
So it only has to be a subset for previous consistent sets, right? Not
Yeah.
all previous sets.
Right.
So it depends on the, so it, every time we would see, okay. Sure.
You're right. I'll probably go through it. Okay. So say this is the set that you see at t equal to 10, and you understand this, so I'll change the emphasis. So at time step t equal to 10, I'm considering languages from L1 to L10. Make sense? These are the languages under consideration. Say this is L1, L3, L6, and L10. So at each time step, I find out the set of critical languages. Make sense? Sequence. I find out the sequence of critical languages. Once I have that, so this is t equal to 10. At t equal to 11, I get W11. Okay, now what I do, I have three cases. So case one is W11 is in all the critical languages. Say W11 is in all these critical languages. That means, say I got this W11. Okay. Oh, and of course I'll add, I'll increase my languages under consideration from L1 to L11. Say at t equal to 11, this is my sequence. No, okay, sequence should be from previous time step. At t equal to 11, I'll consider languages from L1 to LT minus 1. Okay. And I get my new point W11. I check if WT is in all of my in all languages from this critical set, strictly critical set. If it is, then I output the smallest. I select the smallest one. So you see, I'm slowly decreasing the size of the language under consideration. Okay, this is case one. Case two is, say W11 is not inside any of these. So that could happen. Okay, that could this was case one. My triangle was like this inside. Case two is perhaps my triangle is a bit outside. Then what I'll do, I'll discard all these and just do something random and move on. Okay. So because none of this is useful, right? This is
what do you mean by do something random?
like
Choose a random language.
just choose a random language because I don't have any extra information now.
With replacement or without?
With replacement or these are fixed, so
Like we won't, like by doing random, we are not discarding this L1, L3, L10.
oh no, maybe I should say just output L10, just output the last one, or output L1.
Okay, that makes sense.
Like you can't do anything, or output L11. Like whatever information you had is not useful at this point.
Wait, what was the triangle again?
Triangle is LZ, K. the where my data is coming from.
Oh, so there's more languages outside of L1 to L10?
I have a countably infinite sequence of languages. And at time step t, I can't consider the entire sequence, right? So I'm considering L1 to LT. At time step t, I'm considering L1 to LT minus 1.
Okay.
Okay. And there's one more case where, say, since this is a decreasing set, I'll just draw it like this. Say it's something like this.
Wait, why is it triangle decreasing?
Triangle is not like that. Let me draw another one. Okay. My plan was to draw it at the beginning, but I guess I was too lazy. I draw 3.
So this is the unknown language.
This is the unknown language.
Okay.
This is my square at each point.
That's the words you've seen at that point.
Yes, this is WT.
The set of capital WT.
Doesn't W have to be inside?
Yeah. Sorry. Okay. All this inside, but the critical languages, they are a bit outside. So let's say something like this. So if my W11 is here, something like this, then I'll pick the last language the smallest language where it was still inside. Sorry, I'm slow. Okay. These black circles are decreasing in size, right? So obviously, it's possible that I decrease it too much. So if I see if my WT does not lie in all of these languages, and it lies in some of them, because case 2 was it doesn't lie in any of them. So I find the smallest set where it is still inside, and then I'll use this.
So you'll forget all of these, but you'll now start over with this new smallest set.
Right.
That contains.
No, at each time step I'm starting over. Say I just repeat the computation.
Right.
And for t equal to 11, I'll generate from this set.
So it's like I have always a force to shrink my language.
Yes.
As long as it's kind of contradicts with the data, I go back and start with the
Right. So start with the bigger set.
Okay.
Precisely. I think that's a great way to put it, Ali. So you keep shrinking your set, and if you ever find that you have shrinked it too much, you go back. I think this is great. I didn't think about it, specifying it to this way. I think this is awesome. Perfect segue into next 2 sections. So keep shrinking. If shrink too much, go back. Back as in you're going left, like I'm shrinking right, go back. Okay, now some results. So I was thinking of discussing this on hard instance, but we'll skip that.
I just had a question, like, how do you get this ordering for critical sets?
Oh, right, of course. So I am adding one more thing to my computation model, because my computation model could answer queries like this, right? It could answer if the word I see is in any language. And I'll add one more. I'll say I can check this. Is this true? I can check if 2 languages are subsets of each other.
So you do it for all combinations?
I do it from L1 to LT. So I figure out all the languages which are consistent, and then I can do this right. Yeah. So okay, so good point. Thanks, Aram. So the model of computation this time includes both of these. It's possible to remove this, and that's a more involved algorithm. Anyways, okay, back to this. So Okay, we are at time. If I can take 10 more minutes, I can go through most of it, at least the interesting things. So there's this trade-off between validity and breadth. Validity is you are able to generate strings from the true language. That's validity. Breadth is how much of the true language are you able to cover. Makes sense. So as you can see, our breadth will decrease over time, or in this algorithm, it's decreasing over time. And this trade-off. So of course you want valid algorithms, but you also want algorithms that generate as much of the true set as possible, right? And if you are familiar with the LLM literature, they call it, so this shrinking too much thing is called mode collapse, or people study it under this name. The keyword would be mode collapse, where the LLM is not able to generate diverse answers. And of course the other word is hallucination. So if you do not shrink the breadth, hallucination would be generating something which is outside the triangle, but inside your guess. So if you're generating something which is not in the true language, that's known as hallucination. The nice thing about this paper is they give a quantification of breadth. Of course, don't have time to go over it, but they show that it is possible. They argue that it is possible to generate languages which are like 16, which can generate at least 16% of the original language and still be valid. So that's nice, 16%. I think this was interesting, like it's independent of everything. Okay, the main theorems are, there is an algorithm which for all instances is valid, which is this, the KW algorithm. I didn't show you the proof. And there's one more interesting thing. Since you keep going back, you will hit the true language infinitely often. So, which is interesting. So you're not only always generating from within this triangle, infinitely often the language that you are picking from is triangle. And that fact is nice. It becomes important when you're proving things about breadth. Okay. I think rest of it, if you read the paper, you can discuss with me. I would be happy to discuss it. You can also just go through this list. Actually, I don't know if it's super useful. I want to discuss the in-context learning part, or the prompt-based generation part. It should be like quick. So I'll do it in this way. Recall that an algorithm, it's just like a function almost, which takes in a countable set of strings, the set. Okay, how about this? This algorithm will take some string. So string is your problem description, and it will also output a string. So if you're thinking of a graph algorithm like BFS will take the description of your graph, which you can write in strings, right? And it will output the true path, which is also a string. All right, and both these elements are countable. So I want to write a random algorithm. This is not A, this is some random algorithm that you care about. So I want to write a random algorithm using this set. I1, O1, I2, O2, and so on. So I1, I2, I3, and so on. These are this is just a way of looking at it. These are by valid inputs to the algorithm, and O1, O2 are the corresponding valid outputs. Make sense? Each of these instances is finite. So this set is a countable set of strings, right? And so maybe I can just call it a language. So now X is not a countable set of strings. X can be a countable set of algorithms. By the way, all algorithms are countable. So X can be the set of all algorithms. And now the adversary will give you WT, which is say IT and OT. So it's giving you an input, it's giving you an output, so it's showing you how this algorithm might work, right? And everything we talked about applies here. So identifying an algorithm is not possible in general. However, it is possible to generate valid outputs. And the prompt-based generation comes in because you can say IT is the prompt, OT is the valid output. Right.
What was I and 0? I was beta. I was completely zoned out.
So this is O.
What are these things?
Input, output. So I was saying that any algorithm can be thought of as a function which is taking a string and outputting a string.
Mm-hmm.
There are some other requirements, but let's just stick with this for now. So you take some string and you output some string, and then I give the example of BFS. BFS is taking the description of graph, which is string, and outputting the shortest path, which is also a string.
Mm-hmm.
So now what I'm doing, instead of describing the FS in the C++ code,
Mm-hmm.
I'm
But if you describe it by all input-output pairs, then that set can be uncountably infinite.
it's countably infinite.
No.
Okay,
I can have like a.
This is my reasoning. Maybe you can correct me if I'm missing something. I'm just making all this up. I didn't see this in the paper, so it's possible I'm wrong. But so I1 is finite, O1 is finite. You can only give finite inputs to the algorithm, and it has to give a finite output because otherwise it will keep running forever. So this entire thing is finite, and now this is a collection of finite strings, which is countable.
It's like taking a Cartesian product of two countable sets.
Yeah.
I guess we rely on the assumption that we cannot have.
No, it's not that. It's not that. It's not. Sorry.
No, that would be n squared, which would be.
No. It's not. That's true, but this is not that. It's not Cartesian product because that's gibberish.
No, but I'm saying. Okay.
That's not a useful algorithm. Huh?
It's a subset of the Cartesian product.
It's a subset of the Cartesian product.
So the Cartesian product is countable, and a subset of it is also.
Then a subset
Okay.
is countable.
But
Okay,
also
this
it's a
is the
subset of
argument.
strings, and strings are countable. So
Yeah. Right. Okay. I guess Paulis wanted to say something.
Oh, I was just responding to Vlad, like.
Go for it.
I and O are like, we assume it's a subset of natural numbers instead of like real
Yeah.
numbers.
That's
Because you
what
were,
I figured out.
yeah,
Oh yeah. We can't input real numbers
Yeah.
to algorithms.
limitations.
Yeah. Okay, so this was point number 17, and there are certain conditions in the first paper, Kleinberg and Mullainathan, they talk about this framework, and I guess there are nice follow-ups. Okay, to end, I would like to say that there are some obvious extensions. So, for instance, recall that validity was after some point, you are always correct. What if I can make a lot of mistakes, but the density of mistakes I make shrinks? So for instance, if I'm so consider two scenarios. I'm making a mistake at every 10th time step, okay? So I'm making a mistake every 10th time step. That's scenario 1. Scenario 2 is I'm making a mistake every 2 to the square time step, 2 to the power time step. So I make a mistake at 1, 2, 4, 8, and so on. Both cases I make infinite mistakes, but of course the second case is much more desirable. So can we extend this framework to that? Then I was thinking the notions of density, which I did not talk about. I guess maybe Peterman's RL optimality criterion could be used there. Other than that, results are also available for uncountable sets. So X need not be just countable. People have extended it to uncountable sets. Okay, and the paper is super nice. There are a lot of examples, lot of commentary, and I think there's only one section that's technically hard. It was hard for me. Other than that, it's like very straightforward. Nice paper. I didn't talk about two important things. I wrote it here. If you are curious, you can check it out. I think that's it. Any questions?